Hi everyone, this is Unit 3. This is our first chapter on exponential functions. So what is an exponential function? An exponential function takes the form of f of x equals a times b raised to the x. Right? An exponential function is defined as a function that has a variable as an exponent. All right, there's some stipulations we want to include that the a value must not equal 0, or else everything would go away multiplying by 0. B is not 1 or 0, right? If it were 0, again, we don't have a function. If it were 1, we know that 1 raised to any power is 1. So our function wouldn't behave like an exponential. It would behave like a constant function. We also have the stipulation that b is a positive number. If b were a negative number raised to alternating, even and odd exponents, our graph would vacillate between positive and negative. Again, it just wouldn't behave like other exponential functions. So these graphs will have horizontal asymptotes. The non-transformed graph would have a horizontal asymptote at y equals 0. The y-intercept is a point that we're going to use extensively. Again, we're going to plug in any value the value of 0 for x. Anything raised to the first 0 power is 1. So we'd end up with 1 times whatever our a value is to find our y-intercept. We will talk about exponential growth and decay. The big difference here is that growth occurs when that b value is greater than 1, decay when it's less than 1. So when we graph these functions, the transformations we've seen throughout will continue, right? So we have 2 to the x. And in this case, the first one, we move it down 2 units. We know that we're moving it down 2 units because we are subtracting outside of the operation, right? 2 is raised to the x, and then we subtract 2. That will move our graph down 2. Over on part B, now we are subtracting 2 from x. That's going to move our graph right 2 units. Part C, we are multiplying times a negative outside the operation. So this will be a vertical reflection. And when we multiply times a negative in the operation, that will create a horizontal reflection. Multiplying our a value times 3 will create a vertical stretch by 3. And multiplying x in our exponent will be a horizontal compression by the reciprocal of 3, 1/3. So these transformations are the same we've seen with other graphs. They're going to affect our graphs in similar ways. So let's see what that looks like. I'm going to walk through the first 2, and then I'll let you try the next 2 on your own. Obviously, I will share my work with you. When I graph an exponential function, I want to lean on some key values. Whenever I can, I want my exponent to be 0, 1, and 2. In my opinion, as an exponent, those are going to be the easiest numbers we can choose, right? Anything to the 0 power is 1, so 1 minus 2 is negative 2. It's nice to have an exponent of 1 because anything to the first power is itself. In this case, let me write this here. Anything to the first power is itself. 2 minus 3 will leave us at negative 1. And then raising it to a second power, we'll have 4 minus 3 or positive 1. In my opinion, that's enough for this graph. We are going to have a horizontal asymptote at y equals negative 3 due to the downward transformation by 3 units. I'm just going to go ahead and plot those 3 points we found. I like using these points 0, 1, and 2 as an exponent because we end up with integer values, which makes it a lot easier to graph. Once I have those values, I can now sketch my graph, trying my best to hit that curve. Now these graphs will get large very quickly, so we definitely want to make sure we find those values that are critical to the graph. Let me make sure we have everything here, coordinates of at least 2 points, and the equations of any asymptote, so we have what we need. Let's do number 2 as well. Again, I'm going to set up my table, and I want my exponent to be 0, 1, and 2. In this case, that's not going to be too difficult. I'm just going to use as my inputs 0, 1, and 2. When I plug in 0, I get 1 as a result. That 1 is then made negative, and then we add 1 to it, so we get the point 0, 0. When I raise negative 2 to the first power and then make it negative, I will get negative 1 as a result after adding 1. And then 2 to the second is 4. It becomes negative to negative 4, and we add 1 to get negative 3. So our horizontal asymptote would have moved up 1 unit from its usual starting point at y equals 0. And then the 3 values we plot are 0, 0, 1, negative 1, and 2, negative 3. Again, we're going to sketch this asymptotic behavior to the left, and then our right will grow exponentially. And we can see that's what our function will look like. I'll erase some of the extra sketch marks there just to make it a little bit cleaner. Where's our horizontal asymptote? Well, our graph was shifted up 1 unit, so we have a horizontal asymptote at y equals 1. So as usual, I'd like you to try these next 2 graphs on your own. You're going to try 3 and 4 independently. Again, I really urge you to plug in values that make our exponents 0, 1, and 2. Those are going to be our easier numbers to work with. I'm going to pause the video and work these out. I suggest you do the same. All right, let's see how our graphs looked on numbers 3 and 4. So on number 3, as I said before we went to break there, we wanted to create points that allowed us to use exponents that were nice and easy to work with, 0, 1, and 2. Now in this case, our exponent is negative. So in order to accomplish that, I plugged in values for x as negative 2, negative 1, and 0. That's going to allow me to get those integer values, get the shape of my graph, and I can set it up and go from there. When I plotted these points, I got negative 2, 3, negative 1, 1, and the point 0, 0. The vertical shift of negative 1 leads us to a horizontal asymptote of y equals negative 1. On number 4, I had to get creative again, right? My exponent was x plus 3. So what I did is I plugged in values that when I add 3 to them, they get me to 0, 1, and 2. In this case, my input values, my x values were negative 3, negative 2, and negative 1. From there, we got those y values, the f of x values, negative 3, negative 4, and 6. And we find that that horizontal asymptote has been shifted down 2 units from 0 down to negative 2. So let's move on to some discussion about the natural exponential function. If we were to find this value, the natural exponential function, we would find that it lies between y equals 2x and y equals 2 to the x and 3 to the x. But we want to do a little investigation here. So what we're going to do is we're going to use this function here, this expression, where we have 1 plus 1 over n, all raised to the exponent n. If you want to do this with your calculator, you can plug this in your y equals, and again, it would look just as you see it, 1 plus 1 over x raised to the x. If you want to look at these, you can use your table, right? You can start your table at different places. But what you can do is we will try to find a pattern. So what we've done is we've plugged in these n values. We're trying to figure out, as n gets extremely large, where does our graph go? What does our graph do? What a point does it approach? what asymptotic behavior does it follow? So numerically here, we can see that as n gets larger and larger, we don't change by as much as we go. When n is relatively small, like 2, we get 2.25. When n jumps up to 100, we get 2.7048. When we jump to 100 times more of that, up to 10,000, we get 2.718145. And then if we go up to 1 million as an input, we still get 2.718 and so forth, okay? The idea is that we are approaching some critical value. As x approaches infinity, the quantity 1 plus 1 over x to the x power approaches the quantity e, which is approximately 2.718, as we can see from our table. This e is known as Euler's number. He was a famous mathematician, and when we're going to use it quite extensively when we're dealing with exponents and logs, and again next year in calculus. So let's take a look. We can go ahead and graph this quantity. E is just a number. It's about 2.718. So if I wanted to graph this, I could plug in some values to make this make sense. Again, I like using values that will create an exponent of 0. That's my favorite number to plug in. So I'm going to use x equals 3. And I can use x equals 4 as a value that will get 1 as a result. The exponent will be 1. So when we raise e to the 3 minus 3, we get e to the 0 or 1. When we raise e to the 4 minus 3, it's e to the first or e. Well, those points are on our graph. 1, 2, 3, 1. And 1 unit to the right, we get up to just before, about 3/4 of the way between 2 and 3. We still have that horizontal asymptote in our function. I know it kind of felt like we jumped right in on this idea of this term E, but here's where it comes from, okay? There are these interest formulas, all right? And you can see the 3 of them here. I know we've seen these before, right? We have an initial amount, our principal value, in all 3. We have a rate that we are going to multiply as a percentage. We can see in all 3 forms of our interest equation. We have an n value in just one of them. That's in the case where we compound more than once per year. And then finally, we have our t value, which will be our input for all these functions, the amount of time in years that we've covered. This quantity here is the quantity we were just discussing at the top of the page, right? 1 over some value, we used 1 divided by n raised to the n. We kind of throw out the t for this purpose. But the idea, if we say, what happens when n becomes infinitely large? What we're really saying is, what if we compounded interest on some sort of initial investment or whatever? What if we compounded interest every millisecond, right? Instantaneously, over and over and over, not just yearly or monthly or daily or hourly, even more frequently than that? What if we were at every time constantly compounding interest? Well, what ends up happening is that value approaches E. So rather than trying to come up with an incredibly large n value, we can use this third interest formula that will represent when we compound continuously. Right, that's the idea of E. It allows us to calculate if we were compounding interest at basically every single second, or even more than that, what would our investment do? or others are more dependent on more input, more different information. How many times are we compounding? How frequently? So let's look at an example to wrap up this first half of the notes. Here they tell us we want to invest $8,000 for 6 years. We have two options. So in option 1, and we have option 2. In option 1, we get 7% yearly interest. We compound monthly. In the second, we get 6.85% interest, and that's compounded continuously. So let's just kind of walk through the setup on these two and kind of compare them. On our first, our current amount after this 6-year span, well, we're going to take our $8,000, and then we're going to multiply it times 1 plus our rate, which we know to be 0.07. Notice that I converted that to a decimal. We're not using percentage anymore. It's divided by the number of times we compound per year, 12, raised to the 12 times 6, right? In those 6 years, we compound 12 times per year. We end up raising this to the 72nd power. Over on the right-hand side, where we're continuously compounding, we're going to use our third formula. A equals, now it's P to the RT. In this case, our principal is the same. It's still $8,000 times E. Our rate is 0.685, and our T is still in years. This quantity will be multiplied by 6. So if you want to calculate these, you can plug these directly into your calculator. And what we find is the amount on option 1 is $12,160.84. And on option 2, we get $12,066.60. I know that when I learned this for the first time, it felt like continuously compounding would be more powerful than we thought, right? Just a 0.15% interest increase with just monthly compounding is worth more than continuously compounding, right? As we get to higher and higher frequencies of compounding, the added benefit becomes smaller and smaller. So even though we compounded continuously on option 2, that compounding continuously didn't make up for the fact that over every year we were earning a fraction of a percent more. So that's where we'll pause this on part 1. I will check in with you guys on part 2 in a moment.